Hello, this is Mr. Gilmore with the 3.2 SAS Triangle Congruence. Now, in the 3.1 lessons, we began to investigate what it meant for two polygons to be congruent. Well, now what we're going to be seeing today, as we jump into this next lesson, is there a shortcut to proving that there are congruent triangles? And we're going to find the answer to be yes, that there are in fact shortcuts to this. And what this will involve is our very first postulate for this chapter, known as the side angle side congruence postulate, which is what the SAS stands for. So now here's what I want you to do for me. I want you to picture making a list for a triangle. Now, we've talked about this list before. When we talk about a list, it means you're going to measure out, or you find the measures of all the angles, find the measures of all the sides, and you make a list of them. So you start at one of the vertices, and you list out what the angle measure is there. And then you travel to another vertex. But as you're traveling along to another vertex, you list out the side measure. And then when you get to the next vertex, you list out the other angle measure there. And you continue all the way around a triangle, and the list then becomes 6. There are 6 numbers, 6 pieces of information that you need in that list. Now, if I want then to show that two triangles then are congruent, I would have to have 6 pieces of information for both of them and make sure that the 6 pieces of information for one, it matches up with the 6 pieces of information for the other, and then that way I can call the two congruent if they produce the exact same list. Well, that's a lot of information, especially for triangles. Since they're the smallest polygon, 6 is already a lot of information. So the question we ask ourselves then, is there a number less than 6 that would still give us congruent triangles? And the answer is yes. That magic number for us is 3. As it turns out, we're going to be proving several relationships of triangle congruency. We actually begin to look at what we call the shortcuts to congruence, and these shortcuts apply specifically to triangles. Today's lesson, the side angle side congruence, is one of those shortcuts. And so we'll dive into what that shortcut involves, and we'll see how that postulate will unfold for us. Using that postulate, we'll actually then be able to reach into 4 other shortcuts of proving triangles to be congruent. So instead of finding all 6 pieces of information, we're going to see that the magic number for us is 3. Before we get into the side angle side congruence postulate, I do need to state a new definition for us. This definition is called the included angle. So if I were to give you a polygon, let's say this triangle here, ABC, an angle is considered included by a pair of sides that the angle is formed by. So if we look at our triangle ABC, let's say I pick 2 sides. So if I were to pick AB and AC as my 2 sides, what would then be the included angle? Angle A would then be the included angle. It's the angle formed by those 2 sides. I could then rinse and repeat that. What if I were to say, let's pick side AB and side BC? What would the included angle be? It would be angle B, the angle that's sandwiched between the 2 sides or made by the 2 sides. I could then rinse and repeat that one more time. If I pick the last pair of sides, AC and BC, angle C would be the included angle. But at the same time, when I know which angle is included, I also know which angle isn't included. Which I look at this last example, if I were to pick AC and BC again, C would be the included angle, right? This would definitely be the included. But angle A, I could then say not included, right? It's not the angle that's sandwiched between the 2 sides. So when we talk about non-included angle or included angle, we actually can refer that from our diagram and understand which angle is included and which angle isn't included. So now let's jump into what the side angle side triangle congruence postulate says. I hope this is going to be obvious enough. Now in class, what I would have done is try to set up a situation where we would see how the side angle side triangle congruence would unfold. But it really is hopefully obvious enough that I don't have to really force an argument of why this postulate is true. It really should just be pretty obvious. So let's jump into what this says. It says this: if 2 sides and the included angle, there's our new vocabulary word, if 2 sides and the included angle of one triangle equals 2 sides and the included angle of a second triangle, then those 2 triangles are congruent. So let's say that again. If 2 sides and the included angle of one triangle equals 2 sides and the included angle of a second triangle, then those triangles are in fact congruent. So for us, this really is called the side angle side triangle congruence postulate. We're going to shorten it up to SAS congruence, or in other words, SAS, right? We know that by our side angle side congruence, we can call these two triangles congruent. Here is an illustration of our side angle side congruence. Down below, we have two triangles, triangle ABC, triangle RST. I can call these two triangles congruent. And notice we're using our congruent symbol there between, right? Here's our congruent symbol. It's between the two polygon names. And remember how that works is order matters. We need our angles and our sides which correspond to be in the same order in the congruence statement. So triangle ABC and triangle RST are congruent by the side angle side postulate. If you take a look, we have a side here of AB equal to a side here of RS. We have another side of ABC and another side here, ST of RST, that are also equal to each other. And it turns out it's the included angles that are sandwiched between those two pairs of sides that are also equal, which why it satisfies this postulate. It's the side angle side congruence. These two triangles are in fact congruent, and all we needed was 3 pieces of information, not 6, which is why we consider this our shortcut. So what exactly does this shortcut do for us? Well, think about what the implication is of now declaring the two triangles are congruent. If I only start with these 3 pieces of information of each of these two triangles, and I'm able to declare them congruent, this opens the door for more information. How? Because what follows after we know that we have congruent polygons, we know that all their corresponding parts, their corresponding angles, and their corresponding sides have to be equal in measure. What do we call this? We call this CPCTC. It's what we saw in our very first lesson. The corresponding parts of congruent triangles are congruent. Well, these corresponding parts are our corresponding angles and our corresponding sides. So what remains, right, we start off with 3 pieces of information, but by declaring congruency, we now actually have 6 pieces of information. We know that the other corresponding angles and the other corresponding side have to be equal in measure because of our congruency. If we can prove two triangles to be congruent by side angle side, then we can also then invoke CPCTC to declare that the other corresponding parts also have to be congruent to each other. Here's a quick illustration of showing what I mean. So if we see here in this top diagram, we have ABC and RST. If we have A, B, and C and RST be congruent triangles, notice we go from only 3 pieces of information for both of these, okay, to then knowing that all sides and all corresponding angles are equal. That takes us into 6 pieces of information, right? We started with the 3 up above, and we now can conclude 6 because we can invoke CPCTC. Now, the only way we can invoke CPCTC is once we have proven the triangles to be congruent. So these two triangles above are congruent by side angle side, which then means we know all the rest of the corresponding angles and sides also have to be equal to each other. Now, what we're going to do to conclude this lesson is take a look at some basic side angle side congruence proofs. Here is a breakdown of some of how the proofs are going to unfold, how we're going to actually introduce our side angle side congruence postulate and use them to help either do 2 things. Either prove that 2 triangles are congruent, that'd be one thing, or prove 2 triangles are congruent and then invoke CPCTC. That's a second thing we could do. So here are some basic, I'm going to break it down for you in these 3 basic steps. The first step is prove, if necessary, that 2 sides of one triangle and the included angle are equal to 2 sides and the included angle of a second. Why do we want to prove that? Because what we're trying to do is establish side angle side congruency. If I can show that there are 2 sides and the included angle of one equal to 2 sides and the included angle of another, then I can show that those 2 triangles are in fact congruent. Which means then, in step 2, I can declare that the 2 triangles are congruent by side angle side congruence, which then leads us into our very last step. And this last step doesn't necessarily always happen. In some cases, I just simply ask you to prove the triangles are congruent, which means you'd stop at step 2. But for step 3, once you've proven the side angle side congruency, then you have the ability to invoke CPCTC to declare that you have another part another part that's congruent to each other, whether that part be a pair of angles or a pair of sides. We can then declare them to be congruent by CPCTC. So we are going to do several examples walking through some basic setups of proofs using the side angle side congruence. Now, what I've done here is I have our diagram already set up for us. I've got the given statements, I've got the proof statement, and I'm already giving you the statements. So in step 1 and step 2, I'm already explaining, hey, there's a pair of angles we know to be equal, y, and in step 2, we now have a pair of triangles that are congruent, y. And so what we're going to do is answer these questions why. So if you need to pause the video here to grab the information, I would do so. Let's take a look at what we're given. We're given that our segment AC and CE are equal in measure, and also segment BC and CD are equal in measure. So notice that we're given two sides of one triangle are already equal to two sides of the other. Well, what we need then are the angles that are included. What are the two angles that are sandwiched in between the pairs of sides? Well, it happens to be those two angles. Notice anything special about those two angles? Let's look at the question, our part 1. It says the measure of angle ACB and the measure of angle ECD are equal. Why? Well, what kind of angles are there? They are vertical angles, which means by the VAT, the vertical angles theorem, we can declare those angles to be equal to each other. That's why I know those angles are equal, because they are a pair of vertical angles. And what that does for us is it finally satisfies that we have the pair of included angles that are equal. So does this now satisfy our side angle side congruence postulate? It does. We have two sides and the included angle of one triangle equal to two sides and the included angle of the second. So thus, why are these two triangles, ACB and ECD, congruent? Because of our side angle side congruence. And that is a proof. We just proved that those two triangles are congruent by using our new postulate side angle side congruence. Let's do another example. Again, if you need to pause it to grab the diagram and the given and proof statement, please do. Take the time to do that. Go ahead and pause. But I'm going to help you answer these next two questions. See, sometimes we get a pair of triangles that share a common side. We love when triangles share a side. Here's why. Shared things mean equal things. Let's dive into what we're given. We're given that we already have a pair of equal angles, FGZ and HGZ. We're already also given a pair of equal sides. So we have one side of a triangle equal to a side of another, and we've got a pair of equal angles. Well, what we need is to make sure that those angles are the included angles. So that means we have to make sure that the sides that make those included angles are also equal, which means we're focused on our segment here, GZ in the middle. Okay? That segment, if that segment, right, is the segment we're focused on, proving is equal to the other segment of the triangle, then that's the one that forms the included angle. So that's what we're focused on. Do we know in step 1 that GZ is equal to itself? It is. Why? Because of our reflexivity. Reflexivity says, right, and this should be really reflexivity of equality, says that everything is equal to itself. So the measure of GZ is equal to the measure of GZ. And what that does for us, let me show you on our diagram, I can actually mark that with a double hash mark by saying, hey, I know that that segment's congruent to equal to itself, which then means I have side angle side. I know I have these two sides are equal. I have the included angles now being equal, and that second pair of sides, which really is the same side. But they're shared, and we like shared things. Shared things mean equal things. So I can invoke side angle side now to declare that triangle FGZ and HGZ are congruent. So why? Side angle side congruence. And there we have it. We've reached the conclusion of proving that these two triangles are in fact congruent. Let's do one more. This is going to take it a step further. Now, if we take a look at our diagram, right, we've got, again, a set of triangles, and we're given some information about those triangles. We're going to prove that these two triangles are congruent. But notice that in the proof statement, it doesn't say prove these two triangles are congruent. It says prove that angle A is equal to the measure of angle C. Well, to get to the measure of angle A and the measure of angle C being equal, we can pass through the door of congruency. If I can prove these two triangles are congruent, that means all their corresponding angles and corresponding sides must be equal in measure. So I then can declare that by CPCTC, angle A and angle C are equal to each other. So let's see how this one unfolds. Step 1, I know that BM and MD are equal to each other. Why? Well, in the given, I'm told that M is the midpoint of BD, which means this satisfies the definition of midpoint. Now, step 2. I'm already declaring triangle ABM and CDM are congruent. Let's take a look at our given, what we also have remaining. I'm given that AB and CD are equal, and I'm given that angle B and angle D are equal in measure as well. Now notice I just put an arc and a hash. I didn't make the right angle markers because I don't know the right angles. Okay, can't jump to conclusions, but I did mark them as equal. Does this give us enough for side angle side? It does, right? We do have side angle side here, side angle side. It's the included angle, which then means I can declare these two triangles congruent by the side angle side congruent postulate. What does then that lead us into? Now that I know that the two triangles are congruent, I know by the definition of polygon congruence that their lists are identical. So look at our congruence statement. Look at how our vertex A and our vertex C are in the exact same position. Remember, order matters. What's important then about vertex A and vertex C being in the same position? It means I know that their corresponding angles at angle A and angle C must be equal. So in my very last step, I now can declare that the measure of angle A is equal to the measure of angle C. Why? Because of CPCTC, that the corresponding parts of the congruent triangles are congruent. I know that angle A and angle C are equal in measure. And that is a proof in which we take it one step further. We do get the triangles congruent and then we can, from that, declare CPCTC or invoke CPCTC to then show that we know their parts are also equal to each other. So I could also finally, right, I've declared that, right, we can prove that now. Now that the two triangles are congruent, I can call CM and AM equal in measure, and I can also call this angle BAM and this angle DMC are also equal to each other because of CPCTC. So congruence is a door with more information, and we love walking through that door because we take the shortcut. It's having 3 pieces of information that turns into 6. We like that, right? We just doubled the amount of information. This concludes our lesson for the side angle side congruence postulate, and using it in proof. Please be sure to look at the 3.2 worksheet and be working on that. If you have questions, you are to email me. No ifs, ands, or buts. With that, be good and do good.